Good morning, everyone. My name is Dimitris, and I'm a cryptography researcher at Million. I'm happy to present my joint work with Pratik Sarkar from Super Oracles and Nektarios Tsoutsos from the University of Delaware. This work is called Plasma, Private, Lightweight, Aggregated Statistics Against Malicious Adversaries. So today we will focus on the problem of heavy hitters, which is that we want to securely compute the most popular client measurements in a privacy-preserving way. In our setting, we have multiple clients on the left-hand side and two servers on the right-hand side. And we want to somehow aggregate their measurements and compute these heavy hitters. It's safe to assume that when we do a large-scale statistics, some of the clients might start misbehaving. A prominent work that addresses this issue is called Poplar, and Poplar works on the two-server model, and it achieves both correctness and privacy against malicious clients. This means that the malicious client that tries to poison the result will be detected by some MPC checks, and also that the correctness, this way the correctness of the protocol will be preserved, and also the privacy of the honest clients is maintained. One problem with Poplar is that these checks are performed under MPC, so they are relatively expensive. Another issue is that since we're working on the two-server model, if one of the servers is malicious, then they can add some noise to the protocol, and the honest server has no way of actually knowing this. So the result of the protocol will not be correct. As a response to that, we introduce Plasma, and we work in the three-server model. And Plasma solves this issue by introducing the third server, and this way we can assume that one of the servers can behave maliciously, and the honest servers will detect this. Additionally, we still preserve both correctness and privacy against malicious clients, but now instead of doing these expensive MPC checks, we rely on some lightweight symmetric primitives that are called verifiable incremental DPFs. So before we talk about verifiable incremental DPFs, a very brief introduction about DPFs. We mentioned about the client measurements, and we can assume that these are bit strings, and we will encode these measurements as a path along a binary tree where it's everywhere 0, except for a specific path that is ones, and like the direction of this path will essentially encode the client measurement. So going right means 1, then left 0 and 0. So with DPFs, what we can do is that the client can create two keys, send the keys to the two servers, and the servers can use the keys and expand them to actually acquire secret shares of the original client measurement. And what is important here is that these keys are significantly smaller than actually secret sharing the whole binary tree. So as you can see, we have everywhere additive shares of 0, except for the blue path, which we have additive shares of 1. In an ideal world where everyone is honest, more clients will come, they will generate their keys, send them to the servers, then the server will expand the key, aggregate the trees locally, and by aggregating the trees, essentially they have secret shares of the aggregations of the client measurements, and at the end of the protocol they can reconstruct this and compute the final aggregation or heavy hitters in our case. And in this example, we can assume that the heavy hitters are essentially the leaves that are above a threshold. Again, here we have the threshold equal to, but can be whatever. And to interpret this result, assume that we have 9 clients, that everyone had the empty string, then 2 of them, their bit string started with a 0, 7 of them, their bit string started with 1, out of these 7, 4 of them had 0, and so on and so forth. So this was the ideal world scenario. Now, when we have malicious clients, what can actually happen is that in each level of the binary tree, they can actually submit more than 1 non-zero values. And since they send secret shares to the servers do not have an easy way of detecting this. Another attack is that at some specific non-zero values, the client can actually force the value to be significantly higher than 1, the shares of the value. So when you reconstruct, for instance, this thing down here, we get 16 instead of 1, which disproportionately influences the result of the protocol. To defend against these attacks, we have a new primitive called verifiable incremental DPFs. that does two tricks. So the first one relies on related work from Eurocrypt 2022. And essentially the idea here is to verify that at each level of the binary tree, we have a one-hot vector. To do this, when the servers evaluate the trees, the binary trees, at a specific level, what they end up with is these two vectors, y and z, which are vectors of secret shares, and also they acquire some proofs. The idea here is that if the two proofs are equal, the vectors will be one hot when we reconstruct them. The second property of VIDPF is to verify the paths. This means that we want to check that the non-zero values are along the same path, so they are not spread out in the tree, and they are also a correct value. Like in our measurements, we cared about the non-zero values being ones. So what we do here is first we check that the roots are actually a valid measurement. So if we reconstruct the roots, we don't reveal anything because it's a valid measurement. This is the empty string. And we check that the evaluation is actually 1. Next, we can recursively go down the tree and check that the evaluation at each parent is equal to the sum of the evaluation of the children. And this means that the value that we had in the parent is either left or right. Now you can think that it might be split between the two. However, this in conjunction with the previous property that we care if it's one hot actually forces the VIDPF to have the non-zero value either left or right. Okay, going back to our problem. So the double voting, we can take care of it by verifying the one hotness. And for the disproportionate voting, we can do this check between the parents and the children and verify that the value that we have at the root, which was 1, is correctly propagated down the tree. Another problem that related work had is that since we were in the two-server model, a malicious server could actually disproportionate, again, influence the protocol by introducing some additive error. And you can see now that each server works over their own shares, so the honest server has no easy way to detect this. So in this work, we essentially add an extra server, and we work in the replicated VIDPF setting, meaning that we have like different sessions of VIDPFs between the servers, and this way we can check if everything matches at the end. Moving on to experiments, we conduct experiments over both LAN and WAN. And you can see plasma here with the blue, which is this L prime equals 0 means that we did not have any malicious clients there. Then with a green trend, you can see that we have 10% malicious clients, and this is very close in the runtime with the honest clients. And then the related work is higher, takes more time, essentially, especially if when we go for more, when we consider more clients. And another interesting result here that I skipped due to the interest of time is that we did some optimizations to save up on communication. So you can see that although in the LAN we are already faster, when we go to the WAN, this margin actually increases because our communication is significantly lighter than the related work. Lastly, we conducted some monetary experiments in the sense that when we spawn up AWS servers, we care about the uptime of the server and also about the communication. And the communication is the most expensive part. And Plasma was the cheapest amongst the related workers. And this wraps it up.
Okay, we have plenty of time for questions. Do we have any questions?
So on slide 7, you showed those properties that you needed, but for the second property, you need the first. But don't you just need to check that every value is binary? You don't need to check that it's actually one hot? I think that's already sufficient.
So the first check checks at each specific level of the tree. The vector is one hot. The second checks that all the one hot values are across the same path, and also that the value is 1. Does this cover you?
Yes, I understand the properties, but I think that if you just check the second one and you replace the first one with a check that it's all values are binary without counting
Oh, okay. I see,
That
I
would
see, I
already
see.
be sufficient
Got it, got it.
and more
Um,
efficient, perhaps.
But how can you check that all the values are binary?
I don't know.
Yeah, that's the issue.
Thank you for the presentation. I have a question regarding the correctness. You say that in order to handle the malicious server, you add an additional server. Can you elaborate more on how it works?
Yeah, so the idea is that we run a VDPF session. So essentially, the client, instead of generating two VIDPF keys that sends to one to one server and the other to the other server, essentially now we do it 3 times, the same thing. It's like replicated secret sharing, if you're familiar. So now the client will generate 6 keys and send pairs to the servers. Of course, like each session will need different randomness. Yeah, we'll check the final results.
Do we have any other questions? Pardon me. Okay. Oh,
So, do you think it can be scalable to be more than 3 servers?
It could be. The issue is that with VDPFs, or with DPFs in general, the more servers that you use, it doesn't scale very well. So theoretically, you can do it, but like the performance will suffer.
I think we have time for one more question.
You have added one additional server. What if that server fails at a point? Like how you do you consider that scenario in your work? Or
So any of the 3 servers can be malicious. And I skipped this, but the idea here is that you cannot know who is the malicious server, but the honest servers will abort the protocol.
Okay, let's thank our speaker again.
Thanks.